Hello, good afternoon. My name is Igor Drozdovskiy, and I work at European Space Agency at the European Astronaut Center as an expert scientist, and where I'm supporting development of this particular PANGAEA mineralogical toolkit. So to start, I would say that this is actually the main goal of this project was originally to develop a set of hardware and software tools which allows real-time recognition of geological materials. And this is, of course, a team's effort. And our Caves and PANGAEA team consists of scientists, hardware and software developers. We also have people who are involved in the training of astronauts, instructors, so experts in geology, planetary science, mineralogy. And we also have people who are actually doing very important work of working in operations, specifically ground support operation, both for robotics and the human operation missions. And that is allows us to combine all this knowledge, all these skills together to develop something new. My talk would be only on this particular project, but this project as a part, as a model of a tool that we would be presented on Thursday by Leonardo Turki, which has a name Electronic Field Book. And these are tool set that is much more broad and includes different models. The PANGAEA as a program would be also presented on Thursday in the talk of Cesco Sauro from University of Bologna, who is the director of PANGAEA. So let me start by saying that in our view, real-time, non-destructive and accurate mineralogical analysis will be critical in the future space exploration missions, particularly missions which are related to the future human and robotic explorations for the moon and other planetary bodies. And we already have many experiences and many examples where the rovers, for example, are equipped with different types of analytical instrumentation. However, when we are coming to the human exploration, there are a few peculiarities. And one of these is a time critical. And the time critical, it's very significant constraint for this kind of, let's say, operations. And one of the common examples, what I would say that in our view, we think that real-time usage of portable spectroscopic spectrometers would be extremely valuable in the future surface operations and the future surface missions such as the Artemis. It has been already stressed in the different workshops and including in Artemis Science Definition Report that have been already shown, but we need this kind of tools. And we are working on it for quite some time, so I think it would be a good time to present for you what we actually developed so far. So as I mentioned before, this tool set is not just developed now. We are using part of this tool set, what we call PANGAEA mineralogical tool set, during our PANGAEA geological field training, for which I originally is designed for astronauts and then was also added in our trainees, also the developers or engineers, aerospace engineers, or developers of future space mission. What we came after usage of this kind of analytical spectrometers during the PANGAEA campaigns is that we quickly realized the commercial off-the-shelf spectrometers and commercial tools what exist has its own limitations. In our view, we quickly realized that in order to achieve fast and reliable, let's say, recognition of different minerals, and also in order to provide this information in real time, not only to the crew which are next to the instrument, but also to the scientific support room, we need to develop in the same time and test at the same time as working together. Three different important parts. One is a portable spectrometers, which needs to be properly configured and to be able to operate with the software in real time. Second, all the reference information what we have, such as the catalogs, petrographic catalogs, all the meta information which are essential for identification of minerals needs to be also already specifically selected and customized for specific instrumentation. And of course, reference archives. If we're talking about spectroscopy, we are talking about spectral archives. Our idea is that it needs to be really worked very well with the type of instrumentation that we have. And finally, mineral recognition software. So we started with a common software which comes with each of instrument and finished up developing our own machine learning-based software. And finally, in order to have this information data set in real time, we also found a way to integrate all this software in a portable, let's say, computational devices such as electronic field book. But nonetheless, let's start with instrumentation. We started, as I said, with commercial off-the-shelf spectrometers and quickly realized that none of the spectroscopic methods which we choose or spectrometers which we choose are comprehensive enough, allowing to detect all the types of different minerals and rocks that we actually can observe, let's say, on each of the PANGAEA analog, planetary analog sites. Well, of course, we already looked for the minerals which are abundant on the Moon, Mars, and in other planetary bodies and meteorites. So we already knew that the type of instrumentation we selected, either it is vibrational spectroscopic methods or it is atomic spectroscopy methods. Each of them has its own benefits and drawbacks. But it was also became very quickly clear that if we combine, for example, the mineralogical composition with chemical composition, we significantly can increase accuracy. And that is actually became our main motivation behind developing future instrumentation, which can be used as, let's say, portable spectrometers, which can be used not only on the rovers, but also can be used by the astronauts on the field. And fortunately for us, ESA supported us, and actually ESA now initiated the development of these combined portable spectrometers. And this is the efforts which is done with the help of industrial consortium and experts in developing instrumentation. And these instruments are developed in order to be actually used by the crew on the field. So our involvement in this, we provide in additional calibration, we provide for this development also validation samples, and we also develop our software specifically to be used for these instruments when you have different types of spectroscopic methods in order to provide the real-time identification of minerals. Okay, and so, as I said, the part of this is the petrographic catalog. The catalog essentially contains all the necessary essential information in order to recognize minerals and rocks and the composition of these rocks on the field. The second part, spectroscopic database, is a compilation of from the open access archives, which are available, and some of the names of all of you know. But in order to complement these open access archives to the spectra of, let's say, less available minerals, we also did our own measurements. And currently, let's say for the Raman spectroscopy and reflectance spectroscopy, we have about 10,000 spectra for more or less 617 minerals that we have in our planetary analog database. And finally, we also developed our machine learning software. And the main focus on this, as I said, was data fusion. Data fusion is a term used when you combine the measurements from different types of analytical methods in order to provide a better classification. And the choice was obvious for us because we found that machine learning method allow, even though it's very computationally intensive, when we create a machine learning model, this model can actually do, when you have already this model, can provide very fast classification, really in near real-time classification, even in the portable devices such as the electronic field book, which is currently the tablet. So far, to summarize all of this, we have already the software which allows to communicate with the spectrometers, collect all the data from this, allows to do the classification using our machine learning models, and not only providing information on the results of this classification, which is mostly would be not only the minerals and the composition of these minerals, but also provide information of significance of these discoveries, which is extremely important for a person in the field who doesn't have like minutes to understand what specific composition means. So to summarize, the current status of the project, we already have the partly working system, which is more or less consists of three important parts. The first one is a catalog, and currently, as I said, and it shows here, we have 600 something minerals. The most abundant minerals what we can detect on the Moon, Mars, and asteroids is a proxy of the minor bodies. 10,000 spectra for each of these spectroscopic methods, specifically molecular spectroscopy. And finally, you can see some statistics, what kind of, our data set consists. Finally, for the machine learning software, we have currently the machine learning models with different, let's say, systems, which allows to do supervised and semi-supervised classification. Both for the supervised classification and incremental learning, we can actually significantly adapt our machine learning to specific usage of the instrument. Everything is a modular, and we also had a chance in PANGAEA training to test real-time and real performance of our machine learning on the samples which are collected on the field. And we have statistics for the, specifically here, I showed just a combination of the map. And this is, in our view, is the most optimal usage in terms of trying to include information for all the possible minerals at the same time with high accuracy. And as I said, our tool altogether comes as a set. Therefore, we intend to provide not just only classification software. We would like to provide real-time decision support, not only classification of minerals, but also all the necessary information for the crew and science support rooms, so we can quickly make decisions. There are no weeks to analyze this when you're on the Moon. And finally, we also testing this during the PANGAEA training, so we have real-time also experience of getting the comments from the people who are using the software, which is also very important. User experience and user advice is extremely important for us. Thank you for your attention. If you have any questions, you can actually look on all these references or just ask me any questions either at this conference or just send me an email. Thank you.
Thank you.